welcome to tonight's tutorial. We're being hosted at the Code Factory, and if we like this place, we might continue coming here if we're permitted. So my name is Bart Trojanowski, and I'm a contract developer, and I found myself spending a lot of time reading the Linux kernel code. It's a real pleasure to have the source code behind the operating system that I'm working with. Many times, whether I'm developing on Linux or Solaris or Windows or whatever, and I hit a problem, and I hit the end of my source code and I would like to see what's beyond, sometimes that's not available. And with Linux, it is available. And I'm able to walk through the actual functions that I'm calling to see what it is that I might be doing wrong. It's rarely the fault of the kernel, it's usually my use of it. So that's what brought this on. I was also watching some Google videos one time, and I walked across another Linux kernel walkthrough that happened somewhere in California by another lug, and that was inspiring, and I thought it would be nice to do something like that for OCLUG. So here's the table of contents for this evening. We're currently in the introduction stage. I'm going to give some general info about what the Linux kernel is composed of. I'm going to talk about some cool things about the code or some interesting things about the code. And then for the last hour of tonight, I would like you to ask questions and we'll just read through some code. We'll see what's in there. So, introduction. You're here as guests of OCLUG. Later on, our MC, who is gone right now, will be passing around a hat. We would appreciate a donation, but it's not required. And if you want to find out more about OCLUG, if you don't know who we are, there's the URL. The tutorials, as I mentioned, I would like to hold them on a regular basis. Currently, we have that scheduled for the fourth Thursday of the month, except for next month because Ottawa is hosting the Ottawa Linux Symposium, which is an annual event for Ottawa. It's the 11th year, I think, or the 10th year that's being held here, and it just happens to overlap the fourth Thursday. So code walkthroughs, we're just going to read the Linux kernel code. Eventually we might be looking at code from other projects, but that's not my area of expertise, so we'll start with the heart of the kernel of Linux. And the closest thing I can think of to code walkthroughs are poetry events that artists might have, where they read poetry of their own or of other people. So this is Poetry for Nerds. So now we're going to move on to the general information. If you have any questions while I'm speaking, please just raise your hand, let me know, and I'll repeat the question because we only have one mic. In future meetings we might try to get a few more so you can ask the questions yourselves. So numbers. So here are some numbers. Long ago, I think we're up to like 3 or 4 years now, there used to be a development model using stable and development trees. So the 2.4 kernel, which had an even middle number, was the stable series, and the number that preceded it to the 2.3 series was the development series. Once the 2.3 series stabilized, it became 2.4, and then it was released, and only bug fixes and security issues were fixed in that series. And then 2.5 would start, sometimes in parallel, while 2.3 was still ongoing, and sometimes with the birth of 2.4. And 2.5 was the development series, which then became 2.6. And with 2.6, the developers decided that the model was working really well, and they changed a couple of things, and there will be no 2.7 unless there's some major code rewrite. Or they just get to too many numbers on the 2.6 series or something like that. So Linus maintains the 2.6 tree. All the patches that end up going into Linus's tree end up becoming a release that Linus releases. There are releases from Linus's tree about every 2 to 3 months. The current release, the most recent release that Linus has made is 2.6.25. So the 2625 series is now finished. However, certain developers who call themselves the stable team are maintaining a stable series. So every time that Linux releases a .x, they start a new tree called .x.y. So in this case, it's 2625.y, and they will continue applying security fixes and bug fixes onto this tree. So it's similar to the old stable series, except for instead of being reset every year or 2 years, it's being reset every 3 months. So every 3 months there will be a new .y tree. On top of that, Linux also tracks, I don't know if hundreds, but several dozen other trees. Some of the more notable ones are the tree from Andrew Morton, which tracks random things which might get into the next kernel or the subsequent kernel. That recently has been replaced or augmented with 2 other trees, which is Linux Next. So when Linus is releasing 2626, which will be his next release, which I think will be in the next couple of weeks, the Linux Next tree is tracking patches which will be going into the next release, so 2627. Linux Staging is a staging tree for any developer that's working on something that's halfway finished to finished that people may want to start testing. And of course, all of this infrastructure is based on Git, and I can talk about Git another time. Fantastic tool for source code management. So now we're going to talk about the lines of code. There are 20,000 files in the Linux kernel, 20,000 source files, and 9.2 million lines of code. This is in the 2626 upcoming release. These numbers increase by about 10% each year, and there's some documentation in the tree also. There have been projects that convert this documentation to other languages, translate, I guess is the right word. However, all of the documentation in the kernel tree itself is in English. So just to give you an idea of further breakdown of the source code, the majority of the code is actually not in the core kernel. The core kernel is pretty small. This includes things like the allocator and the scheduler and other main facilities. The majority of the code is in drivers, and I think about 55% of the source lines of code are in the drivers. So the rate of change, I'm not sure if you ever read or saw videos of Greg Kohana-Hartman. He often goes around the country, conference to conference, and gives pretty cool quotes of how the kernel is evolving. So these are some numbers that he quotes. 4.5 thousand lines are added every day. So there are several thousand developers, and all of these changes are just getting into the kernel every day. And that's about 2 to 4 changes per hour on average. As I mentioned before, there is a release from the Linus's kernel tree every 2 to 3 months, and there are 2.4 thousand developers. A recent data mining on the Git kernel source tree revealed that about 25% of them are not being affiliated by any company, so they are hobbyists or people that just do it for fun. Here are some numbers, again from Greg KH, and these are numbers that I just got by looking at the tree itself. So currently the kernel supports 25 main architectures. So one of these architectures, for example, is PowerPC. Now PowerPC has several sub architectures or models that it supports, but there are 25 distinct ones. So these are things like x86, Spark, ARM, MIPS, and so on. We support 60 file systems, which is just insane. And these are on-disk storage file systems, not things like proc or sysfs, actual file systems. There are 20 level 2 network protocols, which are supported. There are 50 ATA drivers. Now, so this is a hardware driver that talks to a PCI chip or some kind of other chip that implements the ATA protocol. This includes SATA and ATA. And some of these implement multiple different chips that are similar enough to be grouped in one driver. So that's 300 different PCI devices that we could support on Linux. And about 200 Ethernet drivers. So next section is types of files. C99. The Linux kernel is written in C. And C99 is the most recent extension of the language or revision of the language. It was finalized in 1999, hence the name, and it adds many extensions to C which the kernel uses. We compile with GCC, and GCC comes with some of its own extensions on top of the C99 model, and these extensions are very fully utilized by Linux kernel, so I'll talk about those in a subsequent slide. I have a question here from Brenda. Uh, So the question is which versions of GCC are required and permitted for compiling the GCC kernel, and how do you know when the Linux kernel exceeds what you have or vice versa. So I believe the current requirement is 3.1, or 3.1 was there was a 3.x series which was broken. It generated some questionable code. So it's either 3.1 or 3.2. How do you know? I think you know when it breaks, or if you pay attention to the Linux kernel mailing list, you will be notified. Or if you read the README, I'm sure it's quoted in there. So anything that's currently available on like modern systems will compile the current kernel. I don't think 2.95 or 9.4 will compile the most recent kernel, but any of the 3x series will compile, and any of the 4x series will compile the kernel. So if you get a kernel today, you're pretty safe. The Linux kernel headers, the header C files, will actually detect what kernel you're compiling with, and they will disable and enable features in the code for the compiler that you're using. So it's pretty safe within a certain range, and then if you go beyond that, the compiler might be just lacking, or be too advanced, although I can't see that being an issue. So if the GCC extensions exist, the compiler will use it. If they don't exist, it will avoid them. The kernel is written using a C style that's documented in the documentation directory in the file coding style. It's one I think that's very, very pretty. There are a few things that I don't completely agree with, but for the most part, it makes the kernel really nice to read because the majority of the code has been written against the standard, and at least it's very similar. And the Linux kernel is written in a C that somewhat resembles object-oriented development, even though it's in C, a language that doesn't actually support any OO features. Scripts. There's a portion of the kernel which contains scripts, and here's a breakdown of what's in them. The C scripts are actually programs which are compiled to help in compiling the actual kernel. So they match the platform on which you're compiling the kernel, not the platform that the kernel will be running on. Do you have a question? So the question is that the C99 standard requires cryptic naming of functions and variables. I don't understand. Okay, I have never run into such a restriction. I don't recall naming a variable total as the example has been given. I don't know. I haven't run into it. I'm sure there are a few things, like, for example, keywords that you can't overlap on. Although, I think you can have a variable named struct, but no, I guess not. No, you couldn't have a variable named struct. So the only thing I've seen is when people try to compile C code from the kernel in C++ with a C++ compiler, certain keywords in C++ are actually being used as variable names and structure names and so on inside the Linux kernel, like for example int class, where the class is the variable name. So the C++ compiler will barf on that, but GCC in the C mode will happily compile it. So I'm not sure about total, for example, being a bad variable name. We can do a quick search on the code to find out if there are any variable names called total and to dispel that myth. I don't know of any such restrictions. There are some bash shell scripts which are also used for generating intermediate header files or C code which are compiled, and similarly with Perl. There's apparently one Python script which takes up less than 1% of that of the script totals. Configuration, when the kernel is compiled, you have a choice of what actually goes into the kernel. The kernel can be tuned for the particular task you're trying to compile it for. An example here from the .config file is config_E1000. E1000 is a very common Ethernet chip from Intel, and in this case, equating that variable to M means that this particular driver will be compiled as a module. You could also equate this variable to a Y, which means that the module will be compiled into the kernel and will not be a loadable module. Or you can comment this line out or remove it, in which case the driver will not be compiled at all. Some of the variables permit yes or M or module. Some of them must be included. Some of them can be removed altogether. Some of them you have a choice of including it as a Y or an M or not including it at all. So kconfig is a file type in the kernel, and there are about 400 of them, which defines a language for configuring or defines these variable types. So for example, E1000 is a type of driver. There's a kconfig file under the net directory and drivers, which defines whether this could be an M or a Y or it could be not included. And there are lots of these files spread throughout the kernel, and they provide help on how to configure, and they feed into the configuration system. So the kernel will the configuration system will read through these kconfig files, and it will ask the user that's configuring the kernel to be built how that kernel should be built. So there are 3 different entry points into this, 3 common entry points. There's make menu config, which launches a text interface, a curses GUI, which will ask you questions on which options you want to enable and disable. There's xconfig, which launches I don't know if it's a TK GUI. It used to be a TK GUI. It might be a Qt GUI now. Okay, so it curses, or sorry, it's still a TCL/TK app that asks you which things you want to configure. There's gconfig, which I think by the prefix means it's using GTK, and there's probably a qconfig or a kconfig that configures it using the Qt library. So depending on what you want to see, I myself find myself using the next 3 commands. Well, not the last one so much. More often, old config is a way of reading an old config file you have, and then the config system will only ask you questions about the new features that have been added since the last time you've configured your kernel. So I usually build in the same tree. I use Git to update my repository, which brings all the new source code, and I type in make old config. It reads my old config file, asks me, well, sometimes 1 question, sometimes 100 questions, and I answer those as well as I can, and the configuration phase is done. With menu config and xconfig and gconfig, you're faced with a tree-like structure of questions. So these questions will be grouped based on subsystem. So that you might have a USB subsystem and about 200 drivers in there. If you're configuring a brand new kernel, you can start with that and go to the USB subsystem and configure the drivers you want to see, or you can run make all mod config, which enables all the drivers which can be configured as modules. This feature, I bet, is used most frequently by distributions, by people like Debian or Fedora or whoever else wants to configure a kernel in this way, where you're shipping a binary kernel in a package and you don't know what the end user has. So you want to ship them as many drivers as you can, even though they will not use 99% of them. So in this case, you want to build as many drivers as modules as possible. And the last option is used by people that test the build system. The rand config generates a random configuration file, and then they will build it. If the build fails, they will report a bug. If the build succeeds, they blow away the whole tree. They build a new random configuration. The build system has about 1,000 make files. The make files make is a program in Unix which runs a recipe, and it builds a bunch of or follows a certain rule set, and it builds or executes certain commands in a specific order. I won't get much deeper into that, but there are 1,000 make files spread throughout the code, and they basically compile the source code into binaries. Linux make system has a help option. If you run make help, there's about 100 or 200 line page or pages printed out on the terminal telling you what other commands make will take to build the kernel. So here's an example of how you would build a kernel. I would run make old config and then make all. You can include both of those on the same command line. So at the end of running old config, it will execute make all, and then make all will build all of the modules and the actual kernel itself. And then I would run make sudo or sudo make modules install and install. Sudo is a prefix that you add to a program if you want to run it as root. So installing the kernel itself needs to be run as root. The other operations can be run as U. Probably should be run as U. And that will install the kernel into the /boot directory and the modules into /lib/modules. So the make system also provides a couple of interesting targets like make deb package and rpm package, and those will build shippable packages with the current configuration that you've set for either Debian or an rpm based distribution. So now we're going to talk about the kernel source tree. So the core system, I think this matches the 5% yeah, this matches the 5% I talked about earlier. These are the directories, the things in the left column. These are directories at the top level of the kernel tree. So we have an arc directory, include init, kernel, lib, mm scripts. I put them on this slide on the core system because you cannot build a kernel without including some C code from these directories. They just must be included. The kernel built with just the files found in these directories won't do anything, but these are essential. So you can see that 20% of the entire kernel tree is in the arc directory, but we have 25 platforms. So actually the x86, which includes the 32-bit and 64-bit derivative, only takes up 1.5%. So it actually takes up a little bit more than its fair share of the 25 different architectures, just because there are so many different variants of the platform. It's been around for a long time. So these are the useful components. You can build the kernel without these, but to actually make it do something, you want to include at least some of these. Drivers, as you can see, takes up a big chunk here. And the reason why this doesn't say 55%, I think, is because I included the make files in this count, and I didn't include the make files in the 55%. So the block file system defines a way that you can queue up requests to the hard drives. A block device in Unix is a hard drive device or some kind of a storage device, something that you can perform random access on. The crypto subdirectory includes just ciphers and the cryptographic framework. The drivers obviously includes things that talk to hardware. The FS is a directory of all the file systems. IPC is interprocess communications. This includes things like support for shared memory, semaphores, yeah, things like that. Net is all of the network stack, so this includes things like TCP/IP and Unix sockets. Security is the majority of the security directory is SE Linux, so I don't know why I included under the useful components, but some people like to use SE Linux. Sound are all of the sound drivers. The video drivers and the radio drivers are actually under drivers, so I see maybe sound might be moving into drivers at some point. Virt is a new directory for virtualization, and this includes things like lguest and kvm support, and Zen. The other directories that I left out from the top level are documentation, which has the obvious use, some sample code, and USR, which includes some scripts and code used for generating files at the kernel build time, but I'm not exactly sure why they're not in scripts. And the next section is code. So I'm going to start with variable types. A lot of this is dictated by C99, but the Linux kernel developers also have a shorthand that we'll see. So C99 types are things like bool, char, int, and then we have fixed-sized integers of the signed variety like int8t and uint8t, and all of the other types that you can imagine. Like the pointer, how to store a pointer in an integer entity, and how to store a pointer difference, and that kind of stuff. So the kernel has a few shorthand types, plus types that are derived from the POSIX headers. Things like size t, and the shorthand for int8t would be s8, and the shorthand for uint8t would be u8. Sorry? It's actually defined in the headers, but it might be defined against something that the GCC defines, like __ size t. So we also have a bunch of types which are generated for user space APIs. So in order to not clash with other types which might be defined in user space headers, the kernel APIs are actually defined using these particular types. And the kernel types in the second bullet there are if'd out when you try to include a kernel only header in user space, whereas these ones would be used. Question? The question is if my slides are on the net. They're not on the net, but they will be on the net. And we're also recording this as a slide cast, so you'll get my voiceover with these slides in some kind of a flash format. Attributes. So again, these are the standard C-type attributes. I think I missed a few, but if you've done any C development, you recognize at least const and unsigned and volatile maybe. And I'm sure there are many others, like registered or reserve, something like that. These are ones which are partially defined by GCC and partially defined by the Linux kernel. And ASM linkage and fast call, which is not listed on the slide, are ways of identifying how many registers will be used for passing function arguments when you're calling a function. Inline and no inline are pretty obvious. They're for optimization decisions. No return is a hint to GCC to tell it whether this particular function will return or not, which I can't see being used very often in the Linux kernel. There's aligned and packed, which defines how variables inside a structure or members of a structure will be packed or not packed inside that structure. Read mostly is again a hint to GCC telling it that this particular variable will be written to very seldomly. Question? The double underscore is how it's defined. So this is the, and it is not to clash with other compiler definitions. So for example, I guess aligned might have been defined somewhere at some point by another compiler. I think GCC defines it as __ aligned __, or possibly attribute aligned. So the Linux kernel just picked one that wouldn't conflict. So to repeat a comment from the audience, it is to make sure that if previous GCC compilers or other compilers cannot support this particular keyword, the headers can replace it with nothing, and then it will have no impact on the code. There are also lots of other tags which don't actually generate any code when you compile the kernel. But when you run the kernel with a checker called sparse, which is a static analysis test suite that Linus wrote in his spare time, it will check for correctness of usage of certain variables. So for example, the user tag tags a pointer that came from user space. So it cannot be accessed directly. It can only be accessed through special functions that copy the user space memory into kernel space memory, or you can map that pointer into the kernel memory, but you cannot use it directly. So there are other ones in that group. Question? So the question is about the user API, user space API. Certain headers will define, the question is what these are used for, if they're used for modules or for something else. They're used for something else. Certain headers will define structures or they will define functions, and these functions will get non-C99 types, so not things like int or long. And in that case, the authors of the Linux kernel would like to avoid clashes with possible other definitions of these types, so they have defined their own instead. So you can imagine having a header in your particular project which defines U8, right? And now the Linux kernel wants to give you an API, and they give you a header, and that header uses a function which takes a parameter U8. So now there's a clash because both the Linux headers want to define U8 and you want to define U8 or uint8t, which might come from the libc headers or POSIX headers. You're writing kernel code which has a user space facing API, and in that case you want to use underscore types. And if you want to get the correct description of why that is, Linux had contributed to a flame war of why we have those. So you can Google for those. Structure initializers. We're onto the C99 extensions. The Linux kernel will very often initialize structures in one swoop. So there will be a macro which defines all of the variables which are the initializer for a particular structure use. So in this case, we're going to define a structure, and I'll show you how these initializers work. So we have a struct foo, and we have two members of it. We have an integer and a pointer to a string. So here's one way that you can define a structure. You can initialize this whole structure in one line, essentially, one C statement. So we have a pointer to a function foo, and we want to assign it. I'm questioning if the star is permitted in this case. We want to initialize the structure foo with both of its members, num and string defined. So we're going to make it equal to a brace, and then inside of that brace block we will include .num and .str and assign those variables. So that's one way, and this is when you're declaring the particular variable. You can also initialize it. The other way is to do it later on, and in this case, on the left-hand side, you would either dereference the pointer so that you can assign the whole structure, or if you have a structure foo defined not as a pointer but as a structure, then you can equate it to the same kind of block. So if the struct foo had more members, or if we excluded certain members from this initializer, in both cases they will be reset to 0. So in the second case, where we already have an initialized structure and we're reinitializing it, it doesn't skip over the ones that you did not include in the brace. It will actually zero those out. So a common use case in the Linux kernel will be to hash define a macro which takes the entire block from the first brace to the closed brace, and it will allow you to reset a particular type. Object flavored programming. I was reading an article recently on the net about the OO in Linux kernel, and there was a distinction drawn between object-oriented and object-flavored. Because C cannot possibly provide all the features that are required for proper OO development, the author of this article dubbed it object-flavored programming. So we'll use that here. So we use structs to define classes, and then we instantiate them to form objects. Structs in this case will have a bunch of data fields, which are the member attributes of a class, of an object, and we always, or very frequently, have an ops structure pointer. And the ops structure is like your call table, the V table I think it's called in C++, which defines all of the function pointers to the methods that this particular object can call. The only distinction is how we call the member functions. So in C++, you would just take your object, put an arrow or a dot, and call into a function. We can't do that in C directly. We must also pass the object itself to that function. So here we have an object, a file pointer, which is frequently abbreviated in Linux to FILP, and we're going to call a close method in this function. So there's an op structure, which in this case is f underscore op, and it is a shared structure amongst all of the file objects that implement the same type of files, the same kind of file descriptor, if you will. So in this case, for example, all of the actual real files would share one file structure, whereas sockets might have a different op structure, and they will have a different set of pointers. So the file object must be passed as the first argument by convention to all of the member functions of this particular object. I have a question. So, I will repeat the comment. The comment is that in previous compilers, it was necessary to surround the filp and up to the close in brackets and actually dereference the function. And yes, I've seen that, and yes, I've used it, but it's definitely not required. And I think it is the evolution of C that is responsible for it. And the way that you're mentioning might be actually stemming from ANSI C, so it might have not been required for a long time, but people just weren't aware of it. I have another question or comment? It used to be that the Linux kernel only supported one file system, and the question is why we are using this object or flavored development style. So when the second file system was added, you could have the same file structure for both file systems, but in order to access files under one file system or another, you would have to call a different function. So one way of implementing this particular this scenario would be to have a big switch statement. For every file system, you would have a case statement in your switch, and then you would check which file system this particular file object belonged to, and do a call either into ext3 or into riser or xfs or whatever you had. So since we now support, I think, 60 file systems is what I quoted, this would be a large system, and for every single system call that operated on files, you would have to go through such a switch statement. So it's not very optimal. So in this particular case, what we're doing is we're providing the same kind of POSIX semantics, POSIX API, like this close or open. Actually, open works a little bit differently. But once you have a file and you know which file system it belongs to, you can fill in all of the other function pointers like read and write and send and receive and ioctl and what have you in a particular way that fits with that file system. So it actually uses the implementation of that file system. So we want to have the same interface, the same API, but be able to force the backend to have a different backend implementing those actual APIs. So what I have described is partially VFS, and VFS is actually a lot more complicated than jumping directly into the file system, but this is the reasoning for it, that you want to be able to have multiple implementations of the same interface. In C++ and other object-oriented languages, you will either have reference counting or garbage collection, and then garbage collection has several different flavors. The garbage collection in the Linux kernel, on the most part, is done at the point at which the object is dereferenced for the very last time. There are a couple of cleanup threads which actually implement something that looks like a garbage collector, but there's nothing that does garbage collection for the entire kernel, and the majority of the object-oriented, object-flavored code will actually use reference counting. So what reference counting does is it assigns a count to the object of how many entities out there, such as other threads or other structures, have a pointer currently pointing to this object. And this is very tricky to get right. It's implemented differently in several parts of the code. It might be one of the hardest parts to debug of this entire object-flavored programming, just because it's not provided by the language. It's very much implemented as you go. So here's an example of a base class. K-object is not the superclass of all the objects or object-like entities in the kernel, but it's being heavily used by the sysfs file system, so it's probably the most used class. And in this case, what we're doing is we're calling kObject get, which is a very common semantics. There's a get and a put function to increment and respectively decrement the reference count. And what's actually hidden behind the kObject put call is a dereference, a check if the current reference count is 0, and if the reference count gets to 0, that object will be freed. Possibly a cleanup function will be called to clean up that object. So I think that's all I have to say about that. We'll probably see more use cases of this, if not today, then later on. So macros are like the big wart of C, and they make the code very hard to read. So I'm going to show a couple of tricks that the kernel uses for macros, and some really interesting macros which get used, which I think you should be familiar with. So the one thing that always gets people that come to look at the Linux kernel is the do while 0 construct. And a lot of macros are defined with do while 0, and it's not an invention of the Linux kernel. It just happens to be a way, the only way that you can group several statements and be able to call the macro from any context you want. And there's a thread out there also that describes why this is, and I've seen a formal proof why this is the only way you can group statements together using C, so that you can then call that macro from either an if statement or a for loop, or by having multiple statements called one after another, and so on. GCC also adds another construct which works very similar, which is the bracket brace brace bracket. So any statements you put inside of that will act the same way as the do while 0. It might be a little bit more legible, a little bit less confusing, and it probably isn't supported by the Intel compiler. That's why it's not used. All right, I didn't mention that I think there are only 2 compilers that can compile the Linux kernel, and that's the ICC and the GCC. I haven't heard of other ones being tried. I have a question. So both the do while 0 and the bracket brace brace bracket can be used throughout regular code, but it is most useful when defining it as part of a macro. It doesn't provide anything extra, except for in the do while 0 case. I can see people abusing it by using a break statement, kind of like a goto to shortcut out of the do statement. But it's most likely going to be used when you're defining a macro. So in both cases, those 2 constructs will be used to define a macro that has multiple statements. Again, it provides no value if there's only one line of code inside the macro. So some some interesting, frequently used macros that either GCC defines or the kernel defines to access different types of data. So the first one is the offset of. And this will take a type, like a structure, and a member name, and it will return how deep in that structure in bytes that particular member can be found. The second macro is a container of, and this one's a little bit more tricky, but it's very, very handy when you have subclasses in C. The first parameter is a pointer to a superclass. Sorry. Yes, the first parameter is a pointer to a superclass. The second argument is the type of the of the subclass, and the last one is the member that represents the superclass in the subclass. So here's an example. We have a superclass called bar, and the way that you implement superclass in C, a superclass in C, is you embed the superclass as the first argument, usually inside the subclass. So the superclass-subclass relationship here isn't very interesting, but we have one structure inside another. And we're giving a pointer to the internal structure, and we would like to access something inside the structure that surrounds the internal structure. So below we have a function work on bar, and we're given a bar pointer, and we would like to get the pointer to foo. Well, in this particular case, foo and bar are actually the same pointer, but there's a nice macro which casts that from one to the other. And it works even if there were members before bar inside the foo structure. I'm not sure if I'm describing this correctly. Are there any questions? As a judge, if I'm describing this correctly? Okay, so at the return at the end, the return of the container of macro will be a pointer to foo, and it will have the correct offset adjustment, and it will not generate a GCC warning that you're trying to cast something from one type to another. Next interesting macro is a type check, and what the type check macro does is it asserts inside a macro that one particular argument is of a certain type. And the way this, the reason why this is useful is one downside, one detriment of using macros in C is that while functions, for example, static inline functions, which provide almost the same kind of utility as macros do not do any type checking. And if you want to make sure that the argument that you're passing as a pointer to foo to this particular macro, you can use type check. And it uses some really cool trickery, which I won't get into. We can look at the code later, which makes GCC generate a warning if this is not true. So my next section is on useful functions. Certain things in the Linux kernel API will become familiar, will instantly be familiar to people that have done any POSIX programming. The function printk is very similar to printf in user space. The only difference is it can optionally take a prefix, like in this case, kernel info on the string. Kernel info is actually open angle bracket, I believe 6 or 7, and then close angle bracket. And it's a string, and it gets prepended to hello world in this case, and it's something that gets munged by syslog, and it's placed at the correct severity level when it's being written to log files or put into dmessage and so on. Kmalloc is very similar to malloc from libc. It's prepended by k, and it takes an extra argument. So the kmalloc here is allocating 1024 bytes, and it's being restricted by the second argument. In this particular case, the GFP user is actually the least restrictive flag, but there are other ones which prevent the kernel from sleeping while making the allocation, forcing the kernel to make sure that the buffer that's returned can be DMA'd to and DMA'd from, and so on. KZalloc basically allocates a buffer and also clears it, or at least makes sure it's cleared. And all of the string API, or the majority of the string API that you're familiar with in POSIX, are represented by the Linux string.h file. And they're pretty close. I think in certain versions of Linux, snprintf, for example, would actually blow the buffer if you've given it too much input, and it would not complain, which was interesting. But it would stop once it finished the last argument right. Bit ops. There are certain headers, this one being one of them, that when I'm doing user space development, I always include it from the kernel. Because the API is very clean, it does things quite optimally, and I'm just familiar with how it works. So bit ops operate on any kind of entity that contains bits. It can be a byte, it can be an array of bytes. You just need to give it a pointer. And in the set bit case, we're setting the nth pointer the nth bit in the particular pointer. By converse, there is a clear bit, which does the opposite. There are APIs to find a set bit or find a cleared bit in this array of bits. And there are atomic operations which allow you to test the bit and then clear it. So the pseudocode for test and clear would basically read the value of the bit, then clear it, and then return the bit that was read, but in an atomic way. So these macros are written mostly in assembly, and they're written in such a way for all the 25 platforms that Linux supports that they can be issued safely and not be clobbered between threads. I have another question. The question or statement or assumption here is the question was if we're assuming anything about the pointer or if we're assuming that it's a fixed width. No, the pointer can be of any size you want, and the user of this API should not be calling this function with a number that's beyond the size of that entity. So you can pass it a pointer to a byte. You can pass it a pointer to an array of bytes, or an array of bytes. You can pass it a pointer to a string or a UN64, whatever you want, but the number you pass should not be larger than the number of bits minus 1 within that entity. Another question, comment? It's the machine endian. So it is not something that you can use to shuffle it over the network. It is only consistent within the API. And if you want to know how it's stored for that particular architecture, you would have to look at the assembly language. So it's defined in the most optimal way for that platform.
So it might search 32-bit words on a 32-bit entry.
Right.
The string of bytes as units of 32.
Yeah.
The zeroth as being in the fourth byte.
It's going to use.
It won't be like that. It will go left to right. It will treat integers, bytes, arrays one way. Does that make sense?
No, it couldn't. On a platform where you're given a byte or a UN32, it would have to know what the size is, right? So if you pass it a void star, this API will work. It will not know if it should be scanning a 32-bit entity or a 8-bit entity.
Well, it's not going to take it. It's not going to take into account. It's not going to make a distinction between whether you're actually pointing to a byte of arrays or whether you're pointing to an integer point.
It may not be optimal to search in such a way that fits both a byte, individual byte, and an individual U32 in a most optimal way. So I think there might be certain assumptions. And why don't we queue this up as a question for when we start looking at the code? And we'll look at the assembly and we'll see what the assumption is. The question was whether the pointer needs to be of a particular size, or the entity that the pointer points to needs to be of a particular size. So list is another API that I really like and I use because it defines lists in a way that seems to make sense to me. It's a bidirectional list where the list head is both used as the list entity itself and as a link inside the list. We can talk more about this if you guys have any questions. But basically, it's a bidirectional linked list. So if you have an item that you want to store in the linked list, you define your object, your structure, with the link being the list head structure inside of your structure, and then you call list add. In this case, not the item, but the link inside the item, and a pointer to the list that you want to add it to. And there's a delete operation which removes them. There are the traversal of the linked list is very simple. You just follow the next or the prev pointer. There are several really nice macros that allow you to traverse the list in different orders. Like for example, there's a macro that looks like a for loop where you give it the item that you want to traverse and a pointer to the list, and it will go over all the items. So a clarification on the fourth line, I've made a mistake. The first argument should have actually been dereferencing the link member of the item before passing it to the list add function. Sure. Yeah, this is a fairly clean API. It has lots of different variants, so there was a suggestion that this is a good file to read as on our first day. I have a question or a comment. No, there's nothing done for you in the Linux kernel with respect to garbage collection. Garbage collection is a manual process that you do for your objects. So if you're implementing a new object, you're going to be deciding how the garbage collection, if any, will be done. So if it's going to be basically done as a reference count, and when the last object is dereferenced completely, it's going to be cleaned up. Or if you want to place your objects on a cleanup on a cleanup queue and then clean them up later, that's up to you as the architect of the new object type. Right. So there was a question if this API provided garbage collection, and one of the comments from the audience was that there is no get and put that's defined by this API. This is strictly a linked list. If you define a structure that includes the link item inside of it, that's the only requirement for using it. There's no constructor or destructor used on the linked list. It's just a storage method and a way to go through the list, walk the list. So next thing is about concurrency. One of the ways of locking in the Linux kernel is a mutex. A mutex is a kind of lock as defined by the Linux kernel that can sleep. So if you I haven't talked about this, and I don't think I have any slides for it, so I'll mention it now. There are essentially three different contexts for executing code in the Linux kernel. There is the user context, there is the bottom half context or software interrupt context, and a hardware interrupt context. So going from top to bottom, the user context would be code that's executing on behalf of the user space. So for example, somebody calls read system, the read system call, or they call nyoctl, or somehow they enter the kernel from user space. The service that's executing on their behalf will be executing in a user space, in a user context. And this code can sleep. The next context going down closer to hardware is the software interrupt or bottom half layer. This is what executes the network stack. This layer cannot sleep. So it has to use a different kind of concurrency control, which I'll talk about on the next slide. And the last one is the hardware interrupt, which handles interrupts from hardware. And it cannot sleep, and it cannot be preempted except for from other interrupts using nested interrupts. And it's very restricted in what it can actually do. It can allocate very small buffers. Usually you don't do a lot of computation in this particular context. So mutexes are used in the user context. You will lock a particular region of code, and what you're guaranteed of is that no other code that's restricted by the same mutex will execute either in another thread or on another CPU. There are also some constructs like try-lock, which return a boolean indicating whether the lock has succeeded or not, and I missed a bracket. And if that succeeds, then you're supposed to unlock the mutex. The other concurrency API is implements spin locks, and spin locks can be used, or spin locks do not sleep, at least not unless you've applied the most recent real-time patches. So spin locks do not sleep. Spin locks are used for very tight locking, which means that the stuff that goes between the lock and the unlock is very short. So it's very suitable for synchronizing small blocks of code or synchronizing code which could not otherwise sleep, such as the bottom half context or the interrupt handler context. The first form of spin lock does not disable any preemption and does not disable interrupts. This again can be used for synchronizing two different threads in the user context. And it can also be used for synchronizing two interrupt handlers, or an interrupt handler and a user space context that has disabled interrupts manually, or things like that. In most cases, you will be using this to synchronize two user space contexts. Spinlock BH is used by the bottom half context and any user space context. So if you want to synchronize code that's running at the bottom half context and another bottom half context, or a bottom half context and another user space context, or two user space contexts that do not want preemption to occur, then you can use Spinlock BH. What Spinlock BH gives you is it disables preemption, which means that no other thread or bottom half will break in and preempt your code, and it makes sure that the code that's protected by by this particular lock on another thread or CPU will not execute under the same lock. And the last variant of Spinlock is IRQ save and IRQ restore. There are also a couple of other variants of this, but basically what they do is they disable interrupts and preemption, and then they execute the code. So this is used for synchronizing an interrupt handler and the bottom half, or an interrupt handler and user space, and so on. I think the general rule is if you have code that's executing at a particular context level, you would want to use the spin lock for that context, for the lowest context that's on this list. So if you're executing on the bottom half, you would use bottom half, or IRQ save in this case, but spin lock itself may not be safe. And if you're using interrupt context and you want to synchronize it with anything else, then in both cases you would want to use the IRQ save context. There's a second parameter that goes into the IRQ variant, and that's to store the flags. The particular flag that's of interest here is the interrupt disable flag. When the first spin lock for a particular code path is called with the IRQ variant of the spin lock, it will store the flag so that it's known whether the interrupt should be re-enabled when the lock is released. So these can be nested in all these cases. So that concludes my slides, and now we can start looking at the code. We're going to take a short break, and we'll ask the founder of the Code Factory, where we are being hosted, to give us a brief description of what he does here. So thank you for listening. My intention was actually to write 6 slides. And then I started writing and writing and writing, and I ended up with, I think, 70 or so. So hopefully in a few months, when we meet again, I'll have fewer slides and we'll have more time to look at code. So thank you again, and we'll invite Ian to give us a short talk about the Code Foundry.